So 294 is a topics course. It's a graduate course of which we have plenty this semester. This one is called Program Synthesis for Everyone. If that is surprising, it's because originally it was listed as Programming Language Design for Everyone. But since we put this course on the books, we realized that we can actually teach a superset of programming language design and implementation. The original plan was to do something like 164 for grad students, for PL grad students who don't know the material about language design and implementation, but also for grad students from other areas. And how to do lightweight implementation of languages by embedding them into, in our case, Racket, which is the new phase of Scheme, but potentially into other languages like Haskell if you decide to use a different language in this course. But since then, Emina and I have given a tutorial at CAV on program synthesis, and we realized that we actually know enough about program synthesis and building synthesizers to actually teach a one-semester course and do it for PL students and those who sort of have PL inclinations as well. And so what we're going to teach is sort of a superset, so it's not going to be easy, but perhaps more rewarding. So Emina, who is there, will be co-teaching it with me. We have it perfectly divided. I get paid to do this, and she knows what she's talking about. We are going to record it as a screencast so that I can put it later on the web. This is not so that you can sleep till 12. This is so that other people from nationwide projects and NSF expeditions on synthesis can watch it and follow and maybe participate in the course and perhaps fly in at the end for the poster session and show their projects. You expected to come here and participate in the discussion. So here is the CAV tutorial. If you want to get an idea of what we'll cover, the slides are there as well as screencast of this 90-minute tutorial that was well received. Now we are essentially going to stretch this tutorial, the 90 minutes, into one semester by speaking really slowly.
Well, actually, to be fair, we didn't get through the tutorial in 90 minutes.
All right, so we won't speak so slow. But what we'll cover is basics of modern program verification, not with theorem provers, but with constraint solvers, so those verifiers that are automatic. We'll talk about how to design and embed a language in a host language, in our case Racket, but again, you are free to use Ruby, Scala, Haskell, should all work well for the purpose. Except we'll support this, and you may want to reuse some of the libraries that Emina built. Emina has essentially built a small lightweight synthesizers in Racket called Rosette, and we will be extending it, redoing some of what she did as an exercise. And compared to the sketch synthesizer that Armando Solar-Lezama built as his dissertation with the help of other students, this is probably 100 times shorter, right? I'm guessing.
Yeah, it's very small.
Without being 100 times slower.
Yes, I hope.
Well, by the end of the semester, it will not be slower. It will be faster, hopefully. We'll talk about synthesis algorithms, and we'll talk about sort of software engineering and psychology of programming, where specifications come from. This specification might be the hardest part of verification, but synthesis for sure. So you see this spans a huge chunk of programming languages, from verification to language design and implementation, algorithms, and sort of software engineering. I want to start by involving people in a discussion, because if you don't start now, it will never happen. And I want you to look at two quotes, and then we'll see whether these quotes, which are motivation for the course, actually agree with you. Right? So here, I'll let you read it. The key point is that we automate everything with software, yet software creation is not really automated. Okay? You can read the entire article, but that's the key point. The second point is elaborate a little bit here and say that we do have compute cycles, perhaps 100 times more than when C language was created. But we didn't really harness it in programming. We use it in testing. Clearly, running tests overnight relies on having the cycles to do it. In model checking, which is computationally even more demanding. Somewhat in code generation, in auto-tuning, because you can create code generate different variants of the code, look for one that has good performance, but very little has been done, I would claim, in the front end of programming. You still design with paper and pencil on the board, figure out what the invariants are, data structures, and then you are left with coding it up. And after that, these things help. IDEs are smarter as well. But the job of the programmer hasn't fundamentally changed. So we do have 100 times more performance than when C was created, 1971 roughly. So do we agree that that improvement in performance hasn't really conferred any programmability benefits?
So I guess I would disagree, at least somewhat. I don't know too much about the old days of computing, but certainly a long time ago you had, there was this big supercomputer the size of the room, and you can only use it at night. So you get your punch cards, you punch them in, so you get the job, come back the next morning, and it would crash, and then you'd have to wait the whole day and do the whole thing over again. So just the fact that we all have our own personal computers, you've got a compiler, your compiler runs automatically as you type and modify IDEs. All of that, I'd imagine, gives a fairly big benefit.
Right. So
but
the fact that
was done a long time ago.
The compile cycles are interactive, more or less, is a big improvement, right? But 1970s probably already had many people program interactively, although they may have to come to Evans Hall, which was computer science, overnight. And this is how Unix was born here, that people had few cycles, so they spend the nights here. But you're right. But that's more has to do with availability of computing than the speed, because you could do that interactivity already on slow computers as long as you had a terminal to it. Emina and then Peter.
I would say that probably the most significant improvement is automatic memory management.
Okay, excellent.
It really, really makes life a lot easier, right?
So let's put it under garbage collection. All right. So this is definitely true. It's an example of the languages raising the level of abstraction and certain things being automatic. And yes, not everything is written in Java, C#. People still do a lot of manual, but many, many programs indeed use it. Yes. Peter.
You sort of hinted at what I was saying. Like, if I run Python or some interpreted language, it's interpreted. I mean, there's more overhead, right? I'm okay paying 5x overhead if it's still a couple seconds to run as opposed to half a second.
You're probably paying 30x for Python, but still
it's still sufficient, right?
Exactly.
Because
it is
this 100x improvement. Right?
The job finishes in time. So this sort of fills in this category that we are paying quite a bit of performance for it, but it's okay since now we have some cycles to burn. Okay. There is much more to say about this.
What if you think about like higher level languages like SQL, kind of abstracting away the database implementation?
So SQL, yes, so you can write the higher level languages and compile it into efficient code. I'd say that SQL doesn't really burn those cycles. It probably generates code close to what you would write by hand. So I wouldn't really say that it is the cycles that make it possible. It's the fact that a lot of knowledge was put into a SQL compiler. Although you guys may disagree with me that maybe the SQL schedulers are not that great. So really there have been no other improvements, just raising the level of abstraction and sort of scripting languages 10x or so, we can pay for it now.
The biggest thing I see is that the increased performance allows you to be much more sloppy with architecture. You can get away with an inefficient design today because of the memory power we have, whereas on much lower memory machines and much slower machines, you wouldn't be able to get away with those same designs. Something that you could prototype today using some basic data structures out of your default library, and that may very well be fast enough. You never have to do any tuning on that. That used to not be an option. We used to have roll custom data structures for everything because of the size constraints, and so the performance was so critical.
So essentially you're saying we can afford the overhead of software use, right? We just call libraries, even though writing them by hand could lead to 10x improvement. Again, we can afford. So this is great. So clearly we have used the cycles for better things, for use, for raising the level of abstraction. But I'd say my point remains that at the programmer level, the programming is still pretty much the same. the abstraction has raised a little bit. But we are writing bigger programs, so probably it all washed out in a sense. So,
I actually dispute that point.
okay.
Because the languages haven't changed that much. The libraries have changed massively. And as a programmer, that's the part that sort of most predicts your performance, is the tools you're working with and the things you're combining to build your program. So I think there has been a substantial change in the programmer experience.
Exactly. I'd say that the libraries essentially define their own language, abstractions and operators for composition, so that has raised the level of abstraction. Well, maybe that's the right way to do it, continue building high level of abstraction, but then the problem you face is building compilers from these high level abstractions to efficient code. And why this is more and more important is because we are not going to get these 100x improvements in the next 30 years. At least not until some magical technology will come up. So in fact, if anything, we are going to go back because energy efficiency is going to be more important as we try to shrink our computing into a smaller form factor. So in a sense, we'll be going back to the 70s where cycles were precious. Because you cannot, on small devices that you want to run, afford quite that abundance of cycles. We don't completely agree on it, and I think we understand the point, so let's go on. So what is program synthesis? It can be described by defining some sort of predicate over inputs and outputs of the program that we want, and then stating it as this formula. What the formula says that we are asking whether there exists a program, P, such that for all inputs, the program outputs a value that is a correct output for this input. So if you look at this, what we are saying is that this is a correctness condition. And this is essentially a command to the synthesizer that says find P, or show that P doesn't exist. Okay. That's essentially it. When is it interesting? Well, it's interesting to do synthesis when writing the correctness condition is faster than writing the program itself. If we could write the program itself faster, then who would bother writing the correctness condition? Well, there is a situation when you would do it, and that's when proving that phi is correct is faster than proving that program P is correct. So if you care about correctness, synthesis still makes sense even if writing the correctness condition is hard. Now the next natural question is to ask whether the synthesizer is not just a compiler. And so we could look at this formula and ask ourselves, well, if what we want to do is compile a program into a target program, so go from source to target, is this formula actually still valid? Does it describe compilation correctly? Can we write phi? Can we define it in such a way that the synthesis formula describes compilation?
Can you just have phi accept the compiler as an actual, like the phi returns true if and only if phi?
Well, in this formula you cannot, because if you want to sort of prove that the compiler is correct, presumably that proof involves stating that for all x. Whereas here we have a phi that really looks at individual inputs and outputs.
Sure, but phi could be run on the known compiler, right?
Well, or perhaps if you have an interpreter, we could define it this way, right? Phi x and y could be, you define it in such a way that for this, what do we want to say? Essentially, y needs to equal s of x. So what we are assuming here is that we do have some way of running the source program, perhaps on an interpreter, or you have some operational semantics that somehow evaluates the program on that input, then you check that it is the same as y, which is computed by the compile program. So the conclusion is that this formula describes compilation as well. So what is the difference between a compiler and a synthesizer? Well, it's not easy to draw the line, and in some cases we usually don't care, but it helps us define what is the new about the technology that we want to do. So I'll go over this. So what is a typical compilation? You take your source program, represent it as typically as a tree, abstract syntax tree. And you do it by parsing the source code, doing some name analysis. If you see a variable here, you want to know where it is defined, and maybe type checking if it is a statically typed program. And then you have a tree in some intermediate form that you lower from the source language to the target language, essentially by rewriting the nodes or a little local cluster of nodes until the tree is in the language of the target language, say assembly, or you go from Java to C, whatever. And some of those rewrite rules may look like assign machine registers to variables in the program. That's one way of lowering it. And you do it until the tree is completely in the target language. Now, when you do it, you usually use three rewrite rules. The program could be represented in other formats, such as 3-address sequence code, but it doesn't really change anything. What is important that sometimes you do analysis of the program. For example, you cannot put a variable in a register if some other variable contains a pointer to the variable, because then that variable needs to remain in memory. Okay. So the analysis would prove that such placement of variables to registers is legal. So that's a typical compiler. Now, synthesis, at least the classical one, what we'll refer to classical, is not really that different at the level of the mechanics. You start from a specification stated at some language. We can think of it as a source program. Perhaps it will also be in some AST form. And then the rewrite rules of some sort lower it down into the desired program. Okay. What is different, and this is what makes synthesizers really powerful, is that these rewrite rules need not be deterministic, in the sense that you can apply them and they can rewrite the code into this form or to that form. That essentially leads to many different rewrite sequences and therefore many different programs that you can create. And as a result, you can now explore many different programs rather than being stuck with one deterministic rewrite sequence, which is what compilers typically do. Perhaps more interestingly, these rewrite rules don't need to be composable in a very strict sense that whatever order you apply them, they give you the target program. You could have them, you could define them in such a way that you started rewriting the spec, eventually you could get stuck and say, well, at this point I have no rule to apply, and I'm not yet at the low level in the target language, so you need to backtrack and try some other sequence. Now this gives you quite a bit of additional power, because you can write rules such that you believe, well, there might exist a composition of these rewrites which takes you all the way down to target code, but it doesn't need to be. So these rules could be quite powerful. They don't need to be restricted to be always composable like it's in the compiler. And so, in fact, some of the successful synthesizers have been based on this principle. So let me show you an example. Denali is such synthesizer. These rewrite rules are essentially axioms, and the abstract syntax tree is extended to use so-called E-graphs. Doesn't matter. You'll see what it is. You start with a specification that is essentially a sequence of machine instructions. Here register 6 times 4 plus 1. And we want to see whether there exists an equivalent, semantically equivalent, but hopefully faster sequence of instructions. So you start by representing the program as a tree. Okay? And now you look at the axioms that describe your language. What is the language? It's the language of machine instructions. And this one says that if there is a number that can be written as a power of 2, right, for any n, then you can write it as such a tree. And there is a number that is a power of 2, so it is rewritten into this tree. And this dashed edge says that this subtree computes the same value as this node. It shows equivalence between subtrees. That's why these are E-graphs, essentially connected subtrees. Okay? Now we look at another axiom, which says that if you see such a computation, you can replace it with this node. It's essentially bit shift. Right? And there is such a computation here, right? Because there is register 6. And there is a number that is to the power n. It's here. So we write this and say this is now equivalent. Okay? And you could continue like this and build all essentially alternative sequences of computing this. Okay? And then you run into this rule, which says if you see such a computation, then there is a special instruction on this. This is alpha architecture. And this, in this case, would probably be the fastest way to compute it. Right? So here what you saw is that the fastest instruction, most likely the fastest, the evaluation of performance is done separately by either scheduling it on a static scheduler or actually running it. Did not need to use any other rewrites, you just look at the original tree, but often you need to derive several auxiliary facts before these interesting axioms are triggered. But we got a synthesized program by essentially these rewrites. And you see how we got stuck. We obtained this program which we could not rewrite any further, so in a sense we started exploring other rewrites. So there was backtracking in this search process. What's interesting is that there are two kinds of axioms really that we used. I wonder whether you can distinguish the two categories of axioms there. Can you break it up into two parts? Could help by adding a few more. Okay, so this is how it's broken up, and I can add a few more axioms. So what do these first two define?
Machine level operations.
Exactly. They are machine level operations, so essentially they define the semantics of the target language, right? They are sort of the interpreter for the language, if you will. It's hard to do without these rules. If you don't write them down, it's hard to do any reasoning with the program. So we sort of assume that you always need to have at least those. These are auxiliary rules. This tells you that we want to create sometimes a node for 2 to the power n. This one says addition. Essentially, this one states properties of addition, associativity, commutativity. Of course, those work for integers only. So we have those axioms that define instruction semantics, and those that are various algebraic properties, and often you need those to trigger some optimizations. And the problem with this rewrite-based synthesizer is that often you need to write quite a few of these axioms so that you do arrive at this optimization that you want. But it's hard to see whether you are complete enough. Do you have enough rules that when you push a button, your specification is going to be rewritten into the code that you would like? You perhaps know exactly what code you want. You know what syntactic shape it has. You know that it should have 2 nested loops. It's hard to see whether the rewrites you have would take you into that form. If you do have those rewrites, this synthesizer are fantastic because they are really fast. They only explore programs that are semantically equivalent to the specification, so they never do useless work. In some relatively strong sense, they are great. But these rules are not always easy to write. So, but now that you understand a compiler and a classical synthesizer, we can draw the line. Not that we need to, but people always ask. So I just offer one definition which says that if that thing searches a space of programs rather than follows a deterministic sequence, it's a synthesizer rather than a compiler. And then perhaps more than half of the people in the room disagree, but who cares? We have a definition. So now how does modern synthesis differ from this? Well, in at least 2 important ways. Number one, it's interactive. The previous synthesis was you put a bunch of rules into your rewrite system, write a specification, push a button, it will crank like a compiler, it will spit out the output, right? Now we believe that automation is considered harmful, and in fact the goal is to build systems that are interactive so that you can do a synergy of the human knowledge and the tool knowledge, and of course it leads also to more interesting problems of the dialogue between the tool and the programmer in both directions. Okay? So we can think of synthesis maybe as computer-aided programming. It would be a more correct name, perhaps. Number 2, it's not based on rewrite rules, but on search. Search in a different sense, in that we define a space of programs. Those rewrite rules also define a space of programs, those that you can derive. But our space will be bigger in the sense that there will be many programs that are incorrect. In fact, most of the programs in the space will be incorrect with respect to the specification. But it will be easy to define such space. How? For example, you just write a template with holes in it, and the template defines the space of programs. What's the space? One program for each completion of the template. And so you can write a template which sort of gives a skeleton of an algorithm that has the properties you want. For example, needs to finish in log n steps. or it's a state machine that has so many steps, and so on, that you express, that defines a space, and now you need to find in that space a program that is correct with a separately provided specification. And that search effectively completes the holes in the template, if you will. And how to find that program in that space, and how to define that space, how to do it efficiently, this is what this course is about. But essentially, we'll have a verifier that checks on each program from that space the correctness condition. The challenge, of course, is that those spaces could have 10 to the 100 elements. So I don't know if you want to check them individually, probably not. So we need to find a faster way to check those programs for matching the specification. So a little introduction into the modern style synthesis is you need to take a language, whatever language is suitable for the task at hand. Think of it as you have a domain-specific language for expressing protocols. Could be data log with extension, that could be your starting language. You need to make it now, you need to prepare it for synthesis. First, you need to be able to write a spec. It could be in the same language, could be in another. For that, you usually don't need any extensions. Here, a specification defines a function that computes x plus x. And here is what we call a sketch. It really should be called technically a partial program, a term that Stuart Russell, I believe, invented when he defined ALISP, a language which had this sort of holes for programming intelligent agents. So what does this program mean? Number one, it says that there is a place in the program, you can call it a hole, a placeholder which is substituted with a suitable value, in this case an integer constant, such that a specification phi is met. What is that specification? It's given by this implements clause, which says that after sketch is completed, bar must compute the same value as foo. So you see, this implements clause really defines functional equivalence between the desired program, which is here, right? Clearly one completes the program correctly, and the specification. But this functional input-output spec is not always what is suitable for your domain, because perhaps your programs are non-terminating and they never output a value. They may go through a sequence of states, an infinite sequence of states. So if you really think of it, implements is just a little bit of syntactic sugar on top of safety assertions. So what you really want is think of it as we are adding assertions into the program, and we are looking for values here that don't fail the assertions on any input. Okay. But for programs that are of the functional form, implements is a handy keyword. Okay. So, as I said, we are going to now find the synthesized program as a search over a space defined by this partial program, or a sketch because it's just shorter. And we'll use the specification phi. Again, the specification could be assertions directly in that template. So we are just looking for a completion that doesn't fail any assertions. But this space is large. 10 to the 10 is still reasonable. Often they are much larger. And the way we'll do it is to define the space symbolically, rather than enumerate every element from the space. How exactly to do it? We'll do it symbolically with logical formulas, and we solve those. I'll show you shortly what these formulas are. In fact, I'll show it to you, in one more slide. So how does the system work? You have a spec and a sketch, two programs, usually in the same language. This one has holes in it. This one could have holes, by the way, too. You sort of have non-deterministic specification. You first compile these two programs down to a formula. Now the formula represents a constraint system which you solve, and perhaps h is the variable that represents the value that goes into the hole. You solve it, then you plug h into the sketch, into a relatively straightforward code generator, and now this program P parameterized with 1, so you replace the hole with 1, is the resulting program. That's it. And so each of these we are going to touch on. How to translate this, how to solve it. Not much on that, that's relatively domain specific, but easy. All right, so imagine that you write programs as a formula. Okay, so you represent it as a formula. Let's see how it would be done, and then let's see what we can do with it. So we have a program, a function f that returns x plus x. Imagine that we have a formula with two free variables, x and y, that represents this function f. In this case, y stands for the return value, and the formula simply says y, the return value, equals x plus x. It's straightforward in this case. Now, what can you do with it? Well, first of all, there are techniques on how to encode things like arrays, conditionals, the heap, concurrency, logs, everything. We'll talk about all of these, how to obtain these formulas. Now, if we have the formula, we can use the solver that can accept that logical formula and solve it as an interpreter for the program. Essentially, we can run it, not on the interpreter, but on the solver. How? You take the formula, conjunct it with the input value, x equals 3, you solve for y, and you get the output of the program. Okay? You can do it because this represents the entire semantics of the program. You constrain x. Now we must solve for such a y that it is a correct, valid output from the program. If the program is functional, there is only one y. If the program is deterministic, there is only one legal value of y. Well, what's more interesting is that you can, by representing the program as a formula, use the solver as an inverter of the program. Use the same formula, y equals x plus x. You assert the return value, and now you get the value that is the input which generates such an output. I'm not saying that the program, by the way, must represent an invertible function. If there are multiple inputs x that output y, the solver could produce them all if you ask for the next solution. Okay? So you see how it already can be an inverter without you really doing inversion. You're just solving for the input value that gives you the right output value. Now the interesting part. The interesting part is based on the fact that once we turn it into constraints which are relational, right? If you look back into the formula, this formula doesn't say that you need to compute this and the value falls to y. It just asserts equivalence between the value and the return. So this is bidirectional. You can go in either way. This is what allows synthesis. Now, how do we do this synthesis? Imagine now that we have a formula just like before, where you have input, output, x and y, and now h stands for the whole, which we just lift into the input parameter, h. Okay? So here is a specification, x plus x, and now we have the sketch, x left shifted by h. So the formula here is y equals x times 2 to the h. Now what do we do with it? Well, we pick an input-output pair, and we solve for the value of the whole that gives you a program, essentially completes the sketch such that the completed sketch computes this output on this input. Okay. And so now, after we assert this, the only unknown is h, the wholes, we solved. So you may see a problem here, right? Will this always work?
Only if the program has the form that the programmer specified.
Well, yes, we can only synthesize those programs that the programmer specifies, right? But that's a good thing, because the programmer often knows what program he or she wants, and so writing this partial program is a way of controlling what will fall out of the synthesizer. But is this synthesis algorithm always going to work as nicely as I'm suggesting here? Where would it break down? Well, let me first tell you how did we got these input-output pairs, right? I picked some value x, perhaps randomly, got y by running this program. You see, I didn't even have to convert it into a formula. I just ran it and got 4, which is advantageous because if this program is huge, too huge to be compiled into a formula, I may not be able to turn it into a formula that the solver will scalably accept. But I can, if given an input, always run this on by compiling it, by interpreting it in the usual way, and I get the corresponding output. And now I have an input-output pair. Okay. So when is this going to fail?
We might need more input-output pairs if
we might need more. Why we may need more? Peter.
You overfit, right? Is it possible? Like, you have two larger state space and you end up just
Well, if you
match your examples. But
well, overfitting in this domain would correspond to having so many constraints. I'm guessing that there is no solution here.
or rather, or you have too broad of a sketch, right? And you fit like, you get like basically an if, your input.
You're right. So that seems like you don't actually have enough information, right? And indeed, if I pick 0, 0, which is a correct input-output pair with respect to the spec, I do not have enough constraints from this first line here to actually solve for h. There are many different values of h that meet this constraint, and not all of them are correct with respect to the spec. If they were all correct, fine, you can pick the first one, or iterate over them and see which of the programs is fastest. But in this case, well, we were unlucky in choosing the input-output, and we need another pair. The algorithms for choosing these input-output pairs we'll talk about in the course. There are several. Yes, they are important. It's important that they create a small set of pairs because the constraint system grows as you add them. Emina, did you want to add anything?
No.
You just knew the answer for the slide that you created. So what we call this inductive synthesis in the sense that it relates to machine learning of functions, right? If I give an oracle a few input-output pairs, the oracle will give me a function that agrees with these input-output pairs and hopefully agrees with all the other input-output pairs that I have in mind, but I haven't given it yet. Okay? And so, in the sense, the synthesizer here is an oracle. I give it more input-output pairs, and eventually it will give me a function that I have in mind. Right? So, sort of induce the right solution. Okay? So, what we do, we ask for a program correct on a few inputs. And why on a few inputs? Well, because otherwise, we have the option on somehow dealing with this quantifier and reasoning about all inputs, and there could be 2 to the 256 of them. And that problem becomes much harder. You clearly cannot enumerate them. We just carefully pick a few. Now there is the big question, of course, of how do we know that the program is correct on the rest of the inputs? Well, you can either pray, or you can test, or you can verify, and again, we have choices on how to do it. So there will be a segment on synthesis algorithms in the course, and it would be actually nice if you happen to pick a problem for your project that will lead us to discover new algorithms. Okay, so now I want to transition to what we'll do in the course in terms of projects, format, and so on. And I'll start by asking, why would you look at synthesis now? I don't mean 1150, but I mean 2012. So what are some trends in computer science, maybe last 10, 15 years, that seem to suggest that this technology may be useful? Can you think of some trends? I have 3 on the slides that...
Well, I guess people are like working with more and more data, so just these programs would scale better.
Okay, that's good. I don't have this one, so I like it. Okay, so more data means more scalable algorithms and implementations. We distinguish between algorithms and implementations because often it is quite a bit more work to turn an algorithm into a running, efficient code. But synthesis of algorithms is interesting too, of course. What else has happened in the last 15 years?
We've moved more towards concurrent systems.
Okay, so you could say parallelism, the fact that we need to build hardware that has more components rather than a single faster component. Okay.
Even more.
Right. So, and what's worse, that the parallelism exists at multiple levels. You have SIMD at the lowest level, and then you may have GPUs with many small cores, and you have cores on the chip. Then you may have a cluster of workstations, and that really means you need to take your algorithm and break it down in divide and conquer fashion in accordance with those hierarchies. So, and that's not easy. And then there is concurrency, the fact that these things don't need to go in lockstep, the way it happens in data parallelism, but could run concurrently. You need to synchronize them. if you write them by hand, there could be data races which are hard to debug. The entire, well, you know the story. What else has happened? What makes our life perhaps more exciting, but definitely harder?
I guess people have started caring a lot more about power consumption.
Okay, so let me put it at the bottom. So I'd say energy efficiency. So energy efficiency essentially subsumes parallelism. Parallelism actually came to be as one solution to energy efficiency, because many smaller, simpler cores are more energy efficient than one huge machine that you can build. And so in a similar way, it leads to multi-level machines where you can run many things, perhaps slower, but in parallel.
You could argue that computing environment is more heterogeneous in terms of the platforms and hardware that you want to target. So
okay, so heterogeneity. Okay, yeah. Excellent. This, by the way, I'll throw here. You have choices of should the algorithm run here, or should I break it down such that part of it runs on a GPU, part of it on the main core. Yeah, it's a horrible problem. So how about the web? It means that everything now is distributed. All the computation, right? Your client talks to the cloud, and it's not just data transfer, but essentially the same program running in two parts. Messages could be lost. There are security implications. Okay, so this really goes back to the design of protocols of various kinds, and then programming by non-programmers, scientists who would like to do MATLAB but get high-performance code, not just a prototype of a code, designers, visual web designers, and such, and end users who just want to do their stuff faster, browse the web, and so on. So that really means we want to write programs, or we are forced to write programs that are more complex, and programming itself is more accessible. And part of it we are going to get by designing higher-level abstractions, if we can pay for the high-level abstractions. But often, even in the design of the high-level abstractions, there are still difficult programming choices. So I want to mention two successful real-world synthesizers. The first of them is Spiral. It's sort of, in the classical world, it generates really efficient implementations of linear filters such as FFT, DCT, and so on. It exploits nicely the fact that these problems are divide and conquer decomposing. To do a big FFT, you break it down into some number of smaller FFTs and wire them up just the right way. And what they've done, they invented essentially an algebra for such decomposition. They read maybe 100 papers on FFTs that people have written over 100 years, maybe less than 100 years, but more than 100 papers, and they have written them in such a way. If you want to compute DFT, which I don't actually know what it is, but it's of size 4, you decompose it into one computation of size 2, another of size 2. You compose it with some identity matrix that essentially tells you how you need to move data to it. Then you compose it with some transpose, which sort of swizzles this data around, and then there is another sort of data transformation, which I don't know what it is. The point is that, well, that's part of the problem with these rewrite rules, that I knew at some point what they were, but I don't know right now. The point is that this shows you how some computation of size 4 can be decomposed into smaller computations of half the size, and how these are combined together. And they have a bunch of those, and they explore how to decompose the big problem into smaller ones, all the way to executable code. What is really impressive about Spiral is that not only this algorithmic decomposition is described in the rewrite rules. These are clearly non-deterministic, right? At each level, you may have multiple choices of how to decompose. So the search space is huge. But they also do parallelization and locality optimizations with similar rules. So all fits nicely into one framework. Very impressive work. So you can read about it more here. The second one is flash fill, which I'll try to demonstrate. Let's see if I can zoom it. Okay. So I put here some data. And imagine you want to fill in this column, okay, with the years. You could, of course, write a formula that somehow goes here and call some macros, but of course I don't know the functions. There is something called write, so maybe I could use it that way. Instead, what I'll do, I'll give one example here, and here I just press Ctrl E, and it extracts the years. Okay. Now maybe I want just I want the dates. I do the same. Ctrl E extracts the dates from. It knows which column. Now I want initials of these people. So I do Ctrl E again. Okay. It worked this morning, maybe because these were empty. Okay. Let's see. Well, it did work. That was interesting.
Maybe give it another one.
Well, this column was supposed to need both of them, but let's try. All right, I'll give it JA. Okay, now it works. Interesting. And now I do Ctrl E, and did it right? It didn't quite do it right, did it?
Well, almost right.
Well, almost right, because here I wanted, it got this too. Okay, so how about I now do F2 and I do 28. Okay, and it corrected it. So it is pretty impressive. Now, this one, flash fill, was done by our graduate Sumit Gulwani, who works on various aspects of synthesis, and the story is pretty impressive. He was on a flight back home. He talked to a lady who was on the plane, sitting next to him, struggling with Excel, and she said, "This is impossible." And somehow it became obvious that he works in the field, and he felt compelled to solve it. He went to mailing lists where people posed problems of how do I write an Excel macro for this and that. And he identified sort of a class of problems that would not be too hard to solve. And his synthesizer, the research prototype, does much more than what you see in FlashFill, but FlashFill is now part of Microsoft Office 2013. It seems to be a big success. If you go on the web, you see YouTube videos of some fanboys who show what they can do with it. I'd say it's a success. We'll talk about how the algorithm for FlashFill works as well. What you saw was, by the way, an example of interactivity. If the output is wrong, you can just correct it and it will get more constraints and give you the right program. In a very strict sense, it's probably not a synthesizer because it actually didn't give us, or didn't show us at least, the macro that was synthesized. That's all internal. It would be nice if a macro was produced so that when I add more data later, that macro is just run. It sort of keeps the program internally. It has the benefit that if there are a million programs that are syntactically different but all compute the same thing, the system doesn't need to tell you which of the million programs do you mean, because you don't care. They complete the column the same way, so it could be either of the two. So it sort of limits the interaction. All right, so we're gonna play a little game now. You may now ask, what could be synthesizable? We clearly saw two very different examples, three if you count Denali. And I'd say anything that is a program. By that I mean if you could write the semantics for it somehow by writing an interpreter, compiler, or somehow describing what is the output for an input, it's synthesized. Okay? So to force you to think about it, just look at your laptop and think what programs run on this laptop. Try to take a liberal view of what is a program. And that should tell us what in principle could be one day, maybe by the time we finish this course, maybe later, synthesize it. So the first one.
Okay, like I was thinking you have like syntax highlighting for structured text. Because I have a bunch of text files which are like structured, but you know, like git logs or something, and I want them to be colored automatically. So it's like.
Okay. So we are talking about log structure highlighting. Okay. So you have a highlighter running on your laptop for some languages. Somebody pre-cooked the syntax for it, right? You'd like to do it somehow. Maybe you would like to provide a syntax again as a grammar. Maybe examples would be a better way, right? To provide the specification. More.
You think of like some AI tasks like, you know, I'm shopping online and I want to, you know, only be shown the brands that I prefer, or I'm trying to schedule meetings with people and, you know, don't suggest 4 a.m. in the morning and those kind of work.
Okay. So somehow collect your preferences and help your personal tasks, all right? So maybe let's call it a shopping filter. Okay. A few more.
It could be your like calendar planning. Maybe you have like everyone have like a certain time that want to do something, so it can base on like your past activity and like suggest you that kind of like autofill what you want to do.
So this is sort of, I don't know, well, you can think of it as a sort of a learning system that learns your preferences, but yeah, learning, if it produces a program that you can run or rules that you can evaluate, it is in a sense a synthesizer, so there is a huge overlap between learning and synthesis. Can we be a little bit mechanical about how we look at the laptop and see what's running there? You have one more suggestion?
Yeah, it was unrelated to that, but I was thinking another one would be if you could like look at the source code file and write a program that would format like new code in the same style.
Oh, I see. So it would learn formatting and apply it on the new code. I see. A coding convention transformer sort of. Okay, that's really cool actually. So code convention refactorer. All right. So let me suggest a few. So there is a networking stack. TCP protocol is a program. It inputs some data, the packets, or some acknowledgements in the form of packets, and it sends something back. So you could synthesize protocols. In principle, or really, people actually do synthesize protocols already in this style. There might be an interpreter sitting on it, of say Python. The interpreter embeds or defines language semantics. Considering that an interpreter is a program, you should be able to synthesize an interpreter, and by doing that, you synthesize language semantics. Okay. What else is a program? A spam filter is a program, obviously, so you could synthesize a classifier like a spam filter. This one is not that surprising. Image gallery is running there. There is presumably a compression, decompression. Maybe given a compressor, you could synthesize a decompressor. Okay. A file system is just one big data structure. Maybe you could synthesize more efficient versions of inodes and how they are linked, or maybe you define it and you synthesize methods for manipulating them. Okay. OS scheduler is a program in a sense. Perhaps it's not a functional program in the sense that it accepts an input, produces an output, but it's so-called a reactive program, one of those that always runs, always accepts requests and produces grants something. You could synthesize a scheduling policy that has some good properties. There is a multi-core processor. It's a hardware, but it runs cache coherence protocol. Again, it's a protocol that you can synthesize. It's a program, distributed one, but it is a program. There is a UI, definitely. I don't know what you would synthesize there, but it's a program too. Okay. So now, if you look at this view, do you have ideas on what else you could synthesize?
Well, you can synthesize like UIs for command line programs. So you have some command line utility and it creates a nice little window for it.
Oh, I see. That actually is not a bad idea, maybe. Uh-huh.
You could also possibly create for UI, like write something that I guess creates consistent UI designs throughout an app.
So similar to the coding convention,
right.
you may UIs more to the right. Excellent. Okay, I love it. More suggestions? Well, there will be a homework on this, so you will all have a chance. Okay, so what do we need to synthesize these? What technologies, understanding do we need? Can you throw out a few? What are the prerequisites for making all this possible? Clearly, you could state it at a high level, so you need to take 294. But if we decompose it a little bit, what are the things that we need to learn? Eric, I thought you were ready to say something.
Not to be able to specify properties.
So specifications, okay. There is a lot of freedom here. So we need to know how to write them. We need sort of languages for writing them. They don't need to be textual. They could be graphical. We'll talk a lot about specs. And I hope to actually learn from you a lot about what specs are, because it hinges a lot on that.
To be able to verify them, able to verify properties.
We typically do need a verifier. A tester might be enough, but a verifier would be nice. Oh. Yes, verifier, or at least a verifier. So the verifier should check that these assertions don't fail. You can think of it as equivalence checking between two programs, same language, different language.
How to choose which input-output pairs to use.
How to choose the input-output pairs. So let's say I/O pair selection. This really falls under the algorithms. Okay. So this just tells us the pairs. There is another part of the algorithm, right? Oh, sorry, Ali.
A grammar for the programs to generate.
That's for the programs that you generate or that you accept in the input.
Oh, I was thinking of what's the space of programs. How to.
I see. So essentially, we need, I'll just call it domain-specific language, in which you express maybe the spec, maybe also the partial program, the sketch, right? That comes with the grammar as well as semantics. So perhaps you need an interpreter for it, right? Okay. What else?
Some sort of solver.
Solver, essentially that search itself, right, for the inductive synthesis. We have done it by constraining a few input-output pairs and searching for values of the holes by running a solver. That could be done by just sort of plain backtracking algorithm, the way you actually implemented a couple of years ago, right? You can say it's also a solver, but you don't sort of generate an explicit constraint system and feed it into a solver. So there may be a few more, and how we'll do it is that your project will be sort of a sequence of little milestones that at the end will allow you to go home with a synthesizer for your problem. Like at the end of a summer camp, you go home with your little gadget. It will start with a problem selection. Essentially, what do you want to synthesize? A protocol, a little system for programming by demonstration. Maybe you want to synthesize a specification itself. It's a specification, after all, is an artifact of programming that itself could be synthesizable. Perhaps you have an implementation that is complex. You want to lift it up into a specification that describes it, or some simpler version of the complex code. All that is here. And so you first present what is it that would be cool in your domain to synthesize. Then we'll define a DSL, a language for the domain, so that you don't, because it's crucial to implement specs and partial programs sort of without a lot of clutter. Right? So if you think of a SQL query as being a very concise language for expressing certain operations on the relational data, SQL query is much more compact than writing the same in C++. So for that reason, we define DSLs so that the problems we need to solve are smaller, just like those programs are smaller. The smaller programs lead to smaller formulas, smaller search spaces. So you define a little DSL and embed it in Racket, or if you choose some other language, that's fine. Then the hard thinking will come here, right? Say, define what is your specification, because how you do it influences scalability. Then we'll talk about how to take your DSL and translate it into these formulas. I showed you formulas for x plus x and left shift. Clearly, these are not the hard ones, right? And how to do the translation here. We'll tell you how solvers can help programming, but here is where you can really use your algorithmic compilation thinking, a lot of creativity too. Here is the synthesis algorithm, which is the search, the inductive search, as well as creation of those inputs. And here, by this time, the synthesizer should be running, and chances are it will run too slowly. And here we'll talk about how you can add some redundant constraints to your system to make it scale better. Because sometimes if you tell the solver, oh, I know something. I know that at this point, x should equal y, or x should be greater than y. That property, x greater than y, may be implied by the specification and sketch, but not so directly. So stating that may make all of a sudden the synthesizer scale. Or if you tell the synthesizer, I know I need 3 states to accomplish something, rather than not saying it at all. This is where we'll talk about these tricks. Essentially encoding domain knowledge by adding into the sketch a little bit more, and then we'll have food and demos at the end. So we'll touch on these things. Essentially, we'll define a DSL in here, right? Well, we first start here. What is it that you want to synthesize? Then the DSL, then the spec, the translator, solver algorithm, and then how to write those sketches. That will be the sequence of steps. Okay? Some examples of projects, just judging based on the interest of students here. We may do synthesis of cache coherence protocol or similar, incrementalizer of document layouts, engines, web scraping from user demonstrations, synthesis of biological models that describe how cells behave. Cells are, after all, just programs, if you look at them the right way. And who knows what else. This list is hopefully exciting for you because you will learn from your colleagues, not just from your project. And if you don't really care about using synthesis, although I hope you do, there are open problems that are sort of inherent to synthesis, open problems for the sake of synthesis, from which many projects can benefit. One is how to do interactivity. We don't really know. There is some body of research, of course, on building IDEs and debuggers, but we don't really know how to use these semantic rich tools, analyzers, verifiers, to make some interesting interaction between the programmer and the tool. Well, we have some ideas, but the field is wide open. You know, the compiler mindset is very batch-oriented, so there is a lot one can do here. How to make the synthesis modular? Clearly, we are not going to push the button and a million lines of code falls out. Just like programming, synthesis will be building the program block by block. Even the spiral synthesizer, by the way, which generates sort of 100,000 lines of code, does it in this top-down fashion, right? Divide and conquer division. It starts with FFT for, say, 30,000 bits, and then it breaks it down into smaller ones. And at the end, when it does code generation, they have 100,000 lines of code, but it's not all at once. How to do this? Again, we have ideas, but we don't really know. And then sort of the software engineering, compiler engineering questions of how to build a synthesizer quickly. We have reached a point that we know how to build a synthesizer in a semester. Emina built one, Ali has built one. We can teach you how to do it. It would be nice to do it even faster. And then there are questions of how do you test that it's correct? How do you maintain it? How do you ensure that the properties are right? You saw the flash field demo. It didn't quite do what we expected. Do we know why? So there are many questions of diagnostics of these tools. They should be able to tell you where they got stuck and how. So a ton of interesting problems. So the homework is essentially think of the first milestone. Think of what is a program, what is it you could synthesize, make an intersection between that and the programming problems you see in your everyday life. Or think of them as hardware design problems, whatever. So ideally you suggest a problem from your domain. It doesn't have to be the one that you solve in your project. Then sort of write 3 things. One, the background. Tell us about the problem, because we may not know about what you try to do. Everybody works in a particular domain, say simulator. And what was also the pain point? Second, write the problem statement, say what specific code artifact you want to generate. GPU code? I don't know. And why is it hard to write the artifact by hand? Try to convince us that this is where synthesis should be applied. You don't want to synthesize stuff that is actually very easy for the programmer to write. And finally, a little bit about the specification. What is it that you are willing to say to the synthesizer? We are not asking it how, what formalism, what language, but what is it that you know? Perhaps think of it, if you wanted to outsource this problem to somebody, what is it that would be easy to communicate? Perhaps with a drawing on the whiteboard and half a page of documentation. What's easy to say is hopefully what will turn into a specification for the synthesizer because you understand it well, you feel you understand it, diagnostics should refine your understanding, and you are ready to say it. What you are not able to say should be in the domain of the synthesizer. And next lecture on Tuesday, we'll look at how constraint solvers can help you write programs. You saw sort of a little fragment of it, how the fact that once you represent programs as formula, things become bidirectional between inputs and outputs. And this is how we solve for the holes, which are just inputs. We constrain inputs and outputs, and the holes fell out. That's not the only way what synthesizers can do for you. There are many things they can do. So I'll talk about 4 problems that Emina helped identify. She won't be here on Tuesday, but we'll go over them in more details. And we'll look at some examples of program encodings, and we'll run the Z3 solver, which may not be the fastest for synthesis, but it's easy to use. And so some encodings you should already see on Tuesday. We do have time for a question or two if you guys have some. If you still have enough oxygen, I don't know what we'll do with this room.
So for example, you demonstrated flash fill. So how is the basic ideology different from a machine learning problem? I mean, what is different here?
Well, what is different? Machine learning is very general. You could, of course, phrase the synthesis as machine learning. What's important is what is the artifact that falls out. Right? If the machine learning learns a classifier, something that accepts an object with, say, 20 attributes, knows which attributes to look at, and tells you, oh, this is somebody who is not likely to pay taxes because of this and that. That classifier is, of course, an input, and in a sense that machine learning is a synthesizer too. But in their case, what they synthesized is a program that is essentially like a macro that you could write using some built-in Excel functions, potentially with a few additional ones. So I would say that what is the output of synthesis determines how it's different from machine learning. Okay, thank you, and see you Tuesday.